Okay, hello. Hi, honors class. So far, we've made it through the following, and what we're going to do today is half of, for in this video, we're going to do half of 19. It's called Light as a Wave / Particle. We're actually only going to do the part where we talk about particles today, or in this video, and then we'll finish the other half in a minute. So what you're going to need to prep this page are the following cutouts. You're going to want this one, this one, this one, this one, and this one. There's all of them. So go ahead and pause the video and cut out these 5, and then in a moment I'll show you where they're going on the page. So here's the top part of the page, light as a particle. We'll tape or glue this picture here. The next one will go underneath here. It's kind of a squishy page. So there's light as a particle. But this weird thing, light is actually a wave too, although you can't technically be both at the same time, but light is. It's a little conundrum. So we'll talk about that. So there's the top half, and then here's the bottom half of the paper, where I've got these two. And this one down here. So here's the whole page zoomed out. Light as a particle, light as a wave, picture, 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 picture. So pause the video if you need some more time, and then we'll get going on this top part and how light sometimes behaves as a particle. Okay, so here's a really cool, I don't even know what to call it, image. Light is A, and then if you're looking at it this way, P-A-R-T-I-C-L-E, particle, and then it's got a little particle dot here on the bottom. But you could also look at it this way. Light is A. Here's the W, A, V, E. Light is a wave, and then the exclamation mark has both the particle and the wave in it. So particles and waves are mutually exclusive. You're not supposed to be both. You're supposed to be one or the other. But sometimes when we run an experiment, light behaves like a particle, and other times it behaves like a wave. So the best way I can describe this to you is if you're looking at like a cylinder, a can of soup or something, or a can of soda. If you shine a flashlight, and the flashlight is over here, here's my little marker flashlight. The shadow that you're going to get on the one side of the wall is a square. There's evidence that this is square-like. If we shine the flashlight this way, it's going to make a circle shadow. This is true, this is true. There's evidence supporting both, but the actuality is more complicated. It's kind of how light is. We don't really understand the cylinder, but sometimes the experiment says light is a particle, and sometimes it says light is a wave. So we're going to come at this from both approaches since we don't really understand the actual phenomenon itself in the middle. So the first one, light as a particle. The scientist who found evidence of light as a particle was actually Albert Einstein. So let me write that over here. An experiment called the photoelectric effect was done by Albert Einstein. I'm sure he didn't name it that, but that's what we all call it nowadays. And it showed that light was a particle. Here was the basic setup. So a photon is a word, science word for light, a speck of light. Just like photosynthesis is taking the light, or photography is imaging based on light properties. So a photon is like a grain of light instead of a grain of rice or a grain of sand. So the little light bits are coming in, and this depiction is trying to illustrate that we've got both some wave properties and particle properties. But really, I'm just going to use the word packet since it fits well. So we have photons, aka light packets, coming in. And Einstein would have them hit the surface of a metal. Metal surfaces are not very good at holding on to their electrons. So when the light energy, light packet, full of energy, was entering in, hitting the metal, electrons from the metal itself was getting shot off. So I'm going to label these electron, electron, electron. Kind of like billiards or pool. When one ball hits the other, it like knocks them out. Light in, pow, impact. And the electrons went flying off at some crazy speed. This wouldn't happen. You couldn't have an impact if light wasn't behaving like a particle. So his experiment, called the photoelectric effect, showed evidence that light could behave like a particle due to the impact and loss of electrons from the metal surface. Obviously, when light hit it. You can't really hit it if you're not a particle. So there's the general idea. And he did some variations of that experiment. So here are the kind of different setups. Pause the video if you need, but you're going to want a greenish marker, a colored pencil, and let's see if I can even find the colors I want. Green, red, and purple are the ones that we're looking for, because red is a really low energy color, right? Green is a little bit higher, and the highest color that we can see is purple, highest energy. So these are the colors we want. He did this experiment, and I'm actually going to start out with the red here. In all of these cases, we have a slab of metal, 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 just like down here. And the light is being shown or shoned, cast. The light is being cast onto the metal, just like here, but the artist's depiction is a little different. Red, a low energy color, see how the waves are farther apart? It's really low frequency, so lower energy. This low energy wave didn't do anything. Like, look at the difference between the pictures. I know it's hard to see on the projector, but look at your actual paper. Over here on these ones, something's happening on the side. We're getting the ejection of the electrons, but with this low energy red color, that wasn't happening. No matter if he put 2 red lights or 4 red lights, this just looked like bacon. It didn't matter if he doubled the amount of red light was just too low of a color for this particular metal, and what was happening was nothing. So nothing, nothing. Okay, skipping forward to the highest energy color that we can see, which is purple. We shine a purple laser on here. And the waves are much closer together. It's a much higher frequency wave here. So there's my purple ones. High energy. Now we've got substantial energy coming in. We're like shooting our billiard ball like pa-chow, like lots of energy. And that is important because that high energy, we have to have like enough energy for the impact to be successful and to shoot off these electrons up there. Not enough energy, impact not successful. Here, successful. Notice the difference though when we get to green. Green's kind of a medium color. It's between red and purple, a little bit higher energy than the red. So we'll label this medium energy and green. Green energy comes in, impacts, and it does shoot off electrons, but notice from the image, they are not there. These arrows are like ka-chow on the purple. Very long, very mucho, and here it's like medium, not super mucho. When you have a lot of energy coming in, then you have a lot of energy left over after the impact. When you only have medium energy coming in, then you only have like medium coming out. Let me do some maths here with you. So let's say that our piece of metal, let's say that the piece of metal costs 25 joules for the impact. Red is a low energy wave. If it's coming in with only 15 joules, it doesn't have enough for that impact. Nothing's going to happen. Green is coming with like a little bit more. Maybe green has 50. Green coming in with 50, the impact uses 25. The electrons will be leaving with 25 because 50 minus 25 is 25. The purple one, let me get a new sheet of paper. Same situation, I'm going to use the same piece of metal. Costs 25 for the impact, but purple is like, yes, I have so much energy. I have 100. 100 minus 25. This one is leaving at 75 instead of 25 over here. So there's the difference. There's where our purple ones really, if you didn't already, like make these ones darker, longer, harder, better, faster, stronger, because they have extra energy after the impact. The impact is the same. It just depends on how rich in joules you were coming into that impact. Okay, let's see. Let me check and make sure I got everything. I think so. So let me zoom out. This is the top half of the notes, and in a separate video we'll do the bottom half.